right? We started some discussion about the color model.
Yes, sir. Yes, sir.
Okay. And maybe, I'm not sure, that we discussed up to some point like frame buffer with relationship for the color, and bit wise that distribution for the color gun. That one maybe color map lookup table, right? Up to that, maybe you have discussed.
Yes, sir.
Yes. Okay. So that I just quickly recap. As this is actually related with the two different type of computer graphics and their basic techniques for color display. As you know that beam penetration method and shadow mask method. And we have seen that beam penetration is mostly used for the random graphics or vector graphics, because it depends up to the intensity of the electron beam, how strongly it can fall on the screen. That screen is actually coated with two different colors. Inner one is the green one, the outer one is the red one. And how strongly actually it can fall, that actually give a different combination of the color, and we can see that spot on the screen. Now, the positive thing is actually about this way of generating the color image for the vector graphics is very common and cheap one. However, that the disadvantage, especially, it's can produce very little amount of or combination of the colors. So that's why it's not actually suitable for generating any real life image or shade. Shadow mask method, the common one for actually CRT display that we have seen, or the technique has been applied even in the advanced display for the raster display. That we had a metal disc or maybe a frame in front of actually your color, that phosphorus beam. As you have seen that in common CRT display, we have seen that this delta delta shape, that red, green, and blue, the three primary color, that in a subpixel level, and it can be in a rectangle shape as well in the subpixel level, as you can see on the right hand side. And the electron gun that actually try to through the electron beam, or the intensity of those beam can define according to actually whatever we got in the frame buffer. But it comes through that shadow mask, and through that hole or maybe the rectangle, so that actually it can fall on the screen and can generate the image. Frame buffer, we said a memory, and memory has a very important part for your image actually processing on the screen, because a memory or frame buffer can be considered here for representation in a rectangular shape of that plane, as like a pretty small sheet or plane like that. That is actually a two-dimensional array, that how many they have, maybe so like when I have 16 bit color depth, so that every single pixel has been assigned maybe 16 number of those memory bit. Okay, so that's why bit planes or bit depth or color depth, we have seen earlier, is a number of bits corresponding to the each of the pixel. So any frame buffer resolution, that especially the resolution we do say like, okay, 1280 into 1024. We understand 1280 column, that is the x coordinate on the basis of it that we are considering, and 1024 rows in the y actually axis, that can reach actually that many number of pixels, small boxes, and every box has been assigned for 8 bits, so that you can assume that this resolution can have how much memory can be allocated for it. The 24-bit is actually the true color. We know that if the color gun individually, maybe red, green, and blue, has been assigned with one byte, so that actually 24-bit can be the color depth, and an image in that level, that the number of color it can produce is the highest one that human brain can perceive, okay, or understand. So this is actually the frame buffer, the bit depth relationship. If you have only one bit, definitely you have actually one gun that is actually monochrome, no color in here, red and black and white. And if we have say 3-bit color display, then 2 to the power 3, that means actually 8 colors is possible. As you can see, the combination of them, and individually one bit, so that it represents that if I have a color say like 0, 1, 0, so that 3-bit for one color to define that you need, whereas you have a 24-bit, that time actually you need the 24 number of bits for defining one color. So that if I say it is black, then actually 24 0 is indicating that black, and that's the key, the combination. So every 8 bits here has been actually assigned for one of the gun, so that combined is 24-bit, and these are the number of those colors. That 1,467 like at 77,200. That is maybe the highest number of color that our brain can actually accept or understand the differences. And then we discussed about color map lookup tables. So we are going to discuss a little bit more in detail with solved in a problem that's actually coming at the next. Okay, so let us have the attendance first. Then actually we are coming back. Okay. All right. You just let me know that you are here. Can you please come to the video for a while? Okay, do you have Alif Laila Jannat? Ashikur Rahman Ashik?
Yes, sir.
Ashik Muhammad Alami? Muhammad Alami? Nishat Ara? Nishat Ara? Shoidul Islam Antur?
Present, sir.
Antur. Sumaya Akhtar?
Yes, sir.
Okay, Sumaya. Arifa Akhtar Ritu?
Present, sir.
Umme Janatun Nessa?
Yes, sir.
Okay, Janat. Parvez Alam?
Present, sir.
Parvez. Redwan Ahmed Ratul?
Yes, sir.
Ratul. Salvi Saba?
Yes, sir.
Salvi. Chakaria Hassan Papu? Chakaria Hassan Papu? Maria Mehjabin? Maria Mehjabin? Israt Jahan? Israt Jahan? Abdul Khalik? Abdul Khalik? Rabina Afrin Ami?
Yes, sir.
Okay, Ami. Tajnoba Yasin Esha?
Yes, sir.
Okay, Esha. Shariat Toyon? Shariat Toyon? Hussein Ahmed Antur? Hussein Ahmed Antur? Pratyasha Roy?
Yes, sir.
Okay, Pratyasha Sharnika Das?
Yes, sir.
Sharnika. Khadija Rahman Ria?
Present, sir.
Okay, Ria. Rahat Islam Rupu? Rahat Islam Rupu? Mahmoud Akhtar?
Yes, sir.
Okay, Mahmoud. Didar Al Mahmoud? Didar Al Mahmoud? Tamanna Tabassum?
Yes, sir.
Said Mahmoud Sifat?
Present, sir.
Okay, Sifat. Fairuz Tanjim Achal? Fairuz Tanjim Achal? Sadiatul Nisa Shetuli?
Sir.
Shetuli? Mustafa Iram Uday?
Present, sir.
Yes, sir.
Okay, Uday. Sadia Hussein Mori?
Yes, sir.
Mori? Sadia Akhtar?
Yes, sir.
Sadia? Mantakimur Raman.
Yes, sir.
Okay, Mantakimur. Atik Faisal Imon.
Yes, sir.
Imon. Rahul Devnath. Rahul Devnath. Nishat Taslim Jyoti.
Yes, sir.
Okay, Jyoti. Sadat Mahmud Khan. Sadat Mahmud Khan. Firdausa Hassan Rifat. Minhaj bin Monib.
Yes, sir.
Nahida Islam. Nahida Islam. Asiful Hassan Shamto.
Yes, sir.
Sir, serial 18, sir.
Sharmin Sultana. Sharmin Sultana. Ryan Hussain.
Yes, sir.
Ryan Hussain, are you there? Ryan?
Yes, sir.
Okay, Ryan. Muhammad Alamin.
Yes, sir.
Okay, Alamin. Tariqul Islam. Muhammad Tariqul Islam. And Ashikul Jaman.
Yes, sir.
Okay, Ashik.
Sir, serial 18, sir. Sir, microphone problem এর জন্য বলতে পারতেছিলাম না।
Why you are speaking Bengali?
Oh, sorry, sir.
Sir, Faiz Tanzim Abdul.
Virus Tanjim Achul. So, what is your CL number, Achul?
K.
Toyon, what is your CL number?
Sir, 18.
18. Okay.
Serial 14, sir.
CL Varna. Why is everyone when I was calling the name? Structure. Okay. And Achal, what you said? Sorry, I just missed it.
28.
28. Okay. All right. Anyone else? Many people are sleeping already now, I think.
Sir,
Yes, Ratul?
will you tell us the midterm mark today, sir?
No, I'll give you the script, okay?
Okay, sir.
I don't want to actually spend the time here for it takes actually a lot of time for giving all of you individually the marks silently. It's a little bit difficult. So actually I had a plan last night to upload so that today we can have discussion, but I'll do that in this weekend so that you can get it, okay? The script and Viva mark all will go. I'll just quickly tell one thing about that is necessary. I think in your section the result is better than any other section because I think 1, 2, 3, 4, 5, 6, 7, and 8. Maybe 8 students got in the written more than 90, above 90 marks got in the written exam. I'm talking about actually in one section that none of the students have got even 90 actually in the written exam. In the Viva got better. Usually the overall average mark, if we want to assess, then you will find the Viva mark is more than actually the written mark. It is understandable. Some students actually are still struggling actually for after having average written and also average Viva. That's actually the main concern. Otherwise, your result is actually good. I think I can say like in the written exam, mostly I'm telling about written exam, not about the Viva, because Viva mark actually it's difficult to make a kind of a pattern and tell you. Better just for written. I know that you have more curiosity about it. The highest mark is actually got jointly actually 2%. One is Tasnova Yasin Isha. I'm talking about the written. So it will be changed actually when you put with your Viva mark. And Ashikut Jaman both got 95. They got the highest mark for written especially. Okay. So I hope that you will get the script and the Viva mark. Then you please do that calculation with this written mark, multiply with 0.75 and the Viva mark with 0.25. Then you add the marks. then you will come to know that what actually the mark you have got. And if you can remember your first term mark, then you calculate that out of 40 marks, now how much you have got. And you need to do 20% of them, this mark as well. And then you can actually also make a plan that how much mark you need for your final exam, so that you can reach on your desired actually grade or mark. That is actually, you can also make a plan. Okay. All right, let's move on to our work. As you know that we said that lookup table, in the color map lookup table. Now, what actually it is and why it is necessary, that is commonly the distribution that we do understand how image of every pixel on the screen that we can see, and it has a representation in the memory. Okay, that is actually the main thing that we are going to do. As you can see here that
recording in progress.
The example has been given. The color depth has been actually at first actually it has clearly stated like 12 bit per entry. It has been saying so 12 bit per entry means whatever the color you are going to show, or that has been in the binary format, 12 bit. The memory has been defined maybe for each and every gun for 444 that bit distribution. Now, the intensity value will be defined end of the day with this 444. Like in the example, it says a pixel value with 67 is displayed. That means indicating that 67 is the address. So in a resolution, say like we have 5,000 pixels in there, then 67 number pixel have some color value, and that color value, whenever it has been defined, it has been stored in somewhere, and whenever you raise or you generate that image, that time that pixel take that actually value. According to that, the electron guns actually have that intensity. Okay, like 67, when we said in the frame buffer, that address has been for 67 has been actually defined in here, and then we have seen that in the lookup table they are actually same concept. These two, you can see this is actually the bitmap and this is actually the lookup table. So in the memory you have on that 67 of that address that what actually the value has been stored. The value is 2465. Now what is the bit number? We have 12. So 2465 in the binary that we need to convert, and we will get actually a number like 10011010 and 001. Okay, and this 12 bit, now according to the define that what actually that the bits are distributed for red, green and blue, so that the primary color that has been distribution. So 444, okay, they are mutually distributed. Now first 4 of that binary digit is actually for the red, which is 1001. The second 4 is actually 1010 for green, and third 4 is actually for the blue 001. Now individually that 1001 indicating that this is actually how much for the binary code for in the decimal, that 1 and 1248. So 8 plus 1 is 9. So 9 is actually that we have the intensity value out of 15. Why it is 15? Because this is actually the range now 0 to 15 when you have 4 bit, right? 0, 1, 2, 3, 4 up to that 15. If all 1, that 4 of them is actually 15. So out of 15, we are actually having the intensity value is 9. That means actually what? Around I think 60%, say like it's 60 or 65% intensity for the red cut. Okay, then the green one is actually having that 1010. That means 1, 2, 4, 8. So 8 to 10. So 10 out of 15. So around it's like 70% that of that green gun. And the blue is actually 001. So that is 1 by 15. So that is actually very low, that blue background. So this pixel will actually illuminate with some color combination with red and green mostly, and that will give you a one different combination of color, right? And when we have 2 to the power 12 bit, that means how many possible color is actually can generate a huge amount. Out of that, one of the color is actually this combination. Okay, so this is actually called that video lookup table organization. Okay, so according to the lookup table, that what is the value a pixel have, and that can be actually represent like this way. So we have 3 components, 4 components there actually: the bitmap, the lookup table, the electron guns, and the display. That means in the display. Okay. So in the exam, if you have a question like display color map lookup table with bit plane for the following video lookup table organization, so you just only need to write down that one or draw that one actually, as it is said display. And what actually the value says, it says already the color depth, that 12 bit per entry. Now a pixel with the value have 79, and on the screen, and its lookup table they find out is 2081 is actually the value. Now what should be actually the red, green and blue electron gun, the intensity of them, right? So that is maybe we can find out with an example of this one. So can you see the screen? Just a minute.
Yes, sir.
Let's see the screen maybe, right? No?
Yes, sir.
Okay, so the problem actually says that display color so the problem is said in short, if we just write down that display the color map lookup table. Okay, with bit plane. For the following video lookup table organization. Table organization. Okay, so each table has 12 bit RNG. Okay, and it says the pixel value is 79. Okay, and that is displayed on the screen, which is displayed on the screen with the value of 79, 2081. So which indicate the intensity of values for intensity of red, green and blue color. Okay. Just write down in our own red, green, blue color. That we are going to find out. Okay. Now, out of this actually content, as you can see, first of all, we need to define on the screen that we have, and exactly the 79 of that is we are going to have a frame buffer. The frame buffer will actually have a rectangular box just for symbolic representation, that is. In that box we have frame buffers like in a many number of plane that we do have here. According to the pixel, that pixel in x and y coordinate in the bitmap. So like this is x, this is y, and we have actually that 79. Now definitely everything has been defined in not in decimal, so that actually we can say this is actually that 79 we need to convert. You can automatically for this value actually you can convert it, or not necessary to do not make the calculation. Maybe if you want to do the calculation of the conversion, because it is accepted that during the exam you should not allow actually those type of calculator which can do automatically conversion. Okay, so rather than we do actually the conversion by your own, that 2 divided by 79 divided by 2, and then at the time we find out the remainder. Okay, and that give you the binary number. So 79 we find actually a number with 1100, I think, then 41. Okay, if we check that 1248, then 16, 32 and 64. So 64 and then 8 and 2 is 10. So 8 and 4 is 12. 12 that is 15. So 64 and 15 is actually 79 that you will get. So this is actually my pixel address that is actually related with the lookup table. Okay. As I'm saying, this is my actually bitmap that this is actually the lookup table. In the lookup table that we have maybe row wise. So for 79, so like we have 0 to 255. Now in 79, what actually the value has been written. So if we put down the decimal one, it has been given the value is 2081. Okay. Now this 2081 has been actually defined in the red, green, and blue gun. Okay. So like this is red, green, and blue. Right. So red, green, and blue, and it has been actually now connected with the display. So like in the display that it is giving the intensity value. Okay. And now this red, green, and blue that gun will get actually the value from 2081. So that if we at this case actually you need to do it with the conversion with the calculation by your root, which is 2081. As we know, we will get 1040, right? And then maybe 520, then maybe 210. Okay. Like this way it will go, and finally we get actually that is 1000, then 0010, and 0001. you may also actually identify that how it become the 2081. Here you can see that 1, 2, 4, 8, 16, 32, 64, then 128, 256, 512, 1024, and 2048. So this is actually 2048, and there we can have 1, 2, 4, 8, 16, 32. So we have 32 and 1. If we just add it, then we get 11, 437, and 8, and 2081. Okay, so you need to find out with this. This is important. Do not forget. You need actually the convert the decimal number to actually binary, that by using a process. So you may actually check in any converter or and then you can get the value and just do it. Then actually you will not get the full mark. That is actually the concern. Now this 12-bit, as they are distributed in 444 in red, green, and blue, if we just distribute them in 444, then we got for red is a 100. Then in green we get 0010, and for blue we get 0001. Okay, now this value indicating what? You can see here that it is for red gun, it is we are having now that 100 is actually 1248, so 8, and out of 15 that we have, so 8 out of 15 for red gun. So the intensity we can understand exactly maybe 50%. The green we have actually 0, 1, so 2 out of 15, and that is for green. And the blue is actually 1 out of 15. So actually this is very low that we actually have. So in the pixel that in the box you can see, maybe that is actually that address for 679 is glowing this combination of this color, mostly the reddish, one of the reddish color actually you can see. So you can see that pixel displayed. So here actually we actually do the display at that x and y coordinate that they have has been given. Okay, because the coordinate, according to the coordinate we identify in the here, the address and the resolution if we have, then actually we can identify where actually exactly that is. Only the value has been defined in lookup table, and this is actually the electron guns or red, green, and blue. They are color guns you can say, and here actually it's on the display, right? Do you understand? Very simple. It's nothing complicated, only the display representation. Are you there?
Yes, sir.
Yes.
Yes, sir.
So do you have any question?
No, sir.
No. Okay. So that is about actually the video color map lookup table display. Okay, just do not forget that how a pixel on the screen and color has been assigned, and that color can be actually seen. Okay, that is actually shown in here. Now it depends up to, say, like I'm giving you in a question that okay, 10-bit depth, okay, or our entry should be in 10-bit. Now how do you gonna actually show that on the color gun? Because you cannot do the mutual distribution here. So maybe it should be defined also that red should get actually 4-bit, the green should get actually 4-bit, but the blue should get maybe 2-bit. Okay, so it depends up to that. Now whenever the 10-bit we have maybe say like I have 8-bit color display, then this is also how I can actually define. So maybe I have done in 332, right, something like that, and whatever the combination that we have got, like 10-bit that time, maybe my any color definition should be that 10 combination for the 10 of them, maybe 1 2 3 4 5 6 7 8 9, and so like 10. So this is maybe for 10-bit that we can have. Okay, so red, maybe I am having 3, then as it is 10. So say like red is actually 4, green is 4, and the 2 is actually that for blue. Now what should be the intensity as compared with that? So this is 0 1 0 1, so 1 2 4, so 4 and 5, so that is 5 out of 15 the intensity, right? This one is actually 0 0 8 4 12, 12 out of 15 in the green, and this is actually we got 1 out of how much?
Two, sir.
Hmm?
So 1 out of 2.
1 out of 2. Are you sure? How much actually combination it can create?
So 1, 2 combinations. Sir.
3 combinations, sir.
As it is actually
Yes, sir. Three combinations.
3 combination.
Oh, no, sir.
2 to the power 2, isn't it?
Yes, sir. 4.
Should be 4. How? 0 0 0 1
1
1
0
0
1 1.
1 1, right?
Yes, sir.
So that is actually 0 to 3. So your highest range is 3. So 1 out of 3 actually, that the intensity. Okay, so that's actually can be defined according to the bit. So you see that our natural color has been defined with the 24-bit, mostly that is 888. So 1 byte has been defined on that. Okay, all right. So let's move on to our slide there. So this is actually about the color map lookup table. Then we will try to discuss about the color model. Mostly that chapter is actually defining the color model, and we always actually follow some kind of model, because the model is actually kind of a standard representation, as you know, that actually saying about the color, and it can be defined as a tuple of numbers. Common actually approach, say like when we are saying 1 0 1, 1 for red, 1 for green, 1 for 0 for green, and 1 for blue. So red and blue is actually this color is combined and creating like that. So there is actually a couple of numbers that actually we try to say about the color components, and that create actually a color combination. And you can say like a color model is an orderly system for creating a whole range of colors from a small set of primary colors. So that small numbers you already have seen. We are talking about thousands, millions of color, but only with the primary combination with red, green, and blue, and their actually associated value. And this model, whenever it has been actually represented with some description, right, with these colors like a condition or maybe some kind of shape, then actually this is called a color space. Okay, what is the color space? Just for example, I can show you. This is a color space because the color has been shown with a 3-dimensional cube. Okay, and so every of those segmented point for out of the line or maybe the edges of that cube, it's indicating actually a color. So that's actually called the color space. So viewing condition has been defined in here, that's why. Now this color model actually it has 2 types. Okay, one is actually additive color model, another one is actually subtractive color model. Now additive color model is actually related with the using the light. Okay, to display the color using the light, this is actually the additive color model, and subtractive is actually using the printing inks. Now our uses, that how we are actually using the color with the computer, mostly as it is about the computer graphics, that is actually giving to reverse idea. Okay, reverse, why I'm saying, think about when you are actually talking about in your even this assignment you are doing there, actually you are giving the value for the color. You see that whenever you want actually black, then what do you actually do? You give actually 000 value, right?
Yes,
That
sir.
the absence of the color, that is actually the black that you are giving. But think about the printing purpose, that we wish that if we have this actually model can be used in the printer. Unfortunately, it is not in the real life. It's the object that if you want to see the color, it has to be reflected. Okay, that's why this subjective model or second one is called the reflective one. If you have in your color chart is that red, green, and blue is 000, then actually the page will be printed out with the color. You will find that there is actually white, means nothing is there. Okay, so exactly opposite, as you can see. So defining the computer with the color, that is actually the transmitted light we call. Okay, and the transmitted light is actually called the additive model, or this red, green, and blue, where the absence of them can create actually the black color, but the absence of that in the reflected model, okay, the reflected light or subtractive model, can give you actually the white color. You need all color in the high actually volume so that actually you can get the black color in there. So this is in the reverse mode they have the additive and the subtractive, just remember, or maybe a transmitted light model that which is using. Another one is reflected light model. Okay, now in color model, the purpose of the color model to allow a convenient specification of colors. Okay, now this is hardware oriented color model that we are actually thinking, that two of the model we have said. One is that additive model, one is actually reflective model, or subtractive model. One is RGB one, that is actually the we can see in, especially we can see mostly, that is actually the case that we can see in the computer, that whenever you are doing program, you are actually generating an image and so on. But whenever you taking print out of them, then actually the entire reverse model actually can be used. Now whenever it is in RGB, that means where actually you use in the computer, you use in the camera actually to grab the pictures, you use in the scanner to take the actually pictures or the scanning document with the color. They are using that RGB or the additive model. But whenever it is actually the printing concern that it comes, then actually it is actually the CMY model or CMYK model. Okay, so these are the two of the models that we have. Another model we are going to discuss for the color, that is actually kind of a user oriented model. Okay, user oriented in that sense that which is actually having some feature that maybe can change the color proportion of the image. Okay, like hue, saturation, brightness or value or intensity and so on, that those are actually can be, we have it like you can see in the television when you have this option. Also if you work in the image for actually changing the image pigmentation and all these things, you also actually use this option for as a user. So that's why it's called the user oriented option, and we also actually discuss about that. So these three models especially we are going to discuss. Two of them are directly hardware oriented, another one is actually mostly the user oriented. Okay, so if we go for additive one or RGB, you can see in the right hand side that the image is actually showing that the primary colors, that red, green, and blue, and their combination is also creating the secondary colors, and finally all three can create actually that white color. That is, we understand that if we have actually all three colors high, then we get the white. Okay, now this is additive color model for computer display, mostly the display that we are actually going to use it. You just light to display the color, okay, and result from the transmitted light. Okay, not the reflected, it is the transmitted light, and this all three color can create actually the white color. So in RGB color model, it has the hardware application like PC monitor, camera, scanner, and so on. And CMY color model is used for color printers. Each color can be pointed in the RGB color model as a cube, that already we have shown about in the color space. And red, green, and blue, according to the name itself, they are the primary colors. Okay, and the secondary colors like magenta can be created with red and blue. As you can see here, that red and blue can create the magenta, blue and green can cyan, and the yellow can be red and green. Okay, and also other possible combination can be done, like white can be created one primary color like blue and the yellow from the secondary color. So that blue and yellow, the combination, they can create actually the white color. The same like this one for actually we can go for red and the cyan. Okay, and this is also actually that the magenta, and we can go for green, and the magenta can create actually the white color. So this is also the many way you can do the combination. In the color space, red, green, and blue, they reproduce the other colors. We have seen already this the value or the intensity actually create actually different colors. We can actually give value like from 0 to 1 it can be, or maybe 0 to 255 we also can give actually the value. Both of the cases actually many function in the color related, many function actually allow it. Okay, in the additive color, this is the color space. As you can see that the cube where the x, y, z, those are actually the primary color for three-dimensional space that we can actually define, like black with the no colors, with that in the origin point of that space, where actually the x coordinate is actually have the red, the y coordinate is actually having the green, and the z coordinate we have the blue. So all three is actually this creating that primary colors, and the primary colors they combine and create actually the secondary colors like red and green. So 100 and 010 they combine and create actually 110. Okay, the yellow, or red and the blue, that x and z axis, that 101 is creating the magenta, with the same with green and blue. So y and z is creating the cyan, and all of them actually creating in the white when they have actually the highest 111. So all possible that how many colors we have actually got in here. In that cube, how many colors that we have?
8, sir.
8 color,
Eight
right?
color.
So it is you can see as well the 2 to the power 3, isn't it? So these are the possible 3 colors, and 2 of this model, that additive and subtractive, they have actually that relationship. So when we go for subtractive, you can see that they have reverse, like CM1. CMY is indicating the cyan, magenta, and yellow. Okay, as like the RGB, the printing purpose that we are actually going to use. As it is a subtractive model, you can see here that they are actually the subtractive model, and that red, green, and blue are actually secondary color here as comparing with that condition. Okay, for printing materials you just link to display colors. Okay, and sorry, you just ink to display color, especially we have to use the ink for the printouts, and colors are resulted from the reflected light that we can actually see on the paper that when it is getting printed. Okay, and all 3 color combined and create actually the black color. Okay, as you can see. Now in the colored space, also in that x coordinate is actually the cyan 100, y coordinate has the magenta 010, and yellow is actually having in 001, and their combination like red, cyan, and yellow is creating the green. The blue has been created from cyan and magenta, and the red has been created from yellow and magenta together. And all 3, when they are actually having the highest value, is actually creating that the black. Okay, so this is actually the CMY. We can do a conversion. The conversion process is actually very simple. With the CMY equal to 1 minus RGB, or RGB is equal to 1 minus CMY, as there is the reverse position. So one of the color has been defined in one of the model. We can find out the same color is actually what should be in the other model. Okay. So like the red color in the written in RGB is 100. So in CMY what it should be? Okay, so that if we put that in CMY is an CMY and 111, they are also in one-dimensional actual matrix has been shown for easier to do that. And that RGB, now in RGB we have actually 100. So if we do that subtraction, then actually we get 011. That means actually the magenta is and the yellow has been created. Magenta and yellow has been created the red color, okay, for the CMY. So if you have something like that, then actually you need to find out the, like CMY has been given. Now you need to find out in RGB, and if you find out the RGB, then also actually show that in that space of that color, okay, that where actually it is. Do you understand what I meant? Like this example, if we consider that the magenta has been said in CMY as 010, okay. Now what it should be in the RGB. So I'm going to find out what it should be in the RGB, and also I'll draw the RGB color space and will show that where that magenta is, okay. And for that we say it like in 010, that is the CMY equal to 1 minus RGB. So 111 and the RGB, I take RGB in this side and CMY in that side, so that we got 111 and that's 010. So if we do the subtraction, we get 1, that is 0, and this is 1. So 101, that means red, green, blue. So out of red and blue is actually creating the cyan color. Then also you need to show in that space for that RGB, because you have find out in the RGB. So that the cyan you have got actually that blue, and actually the green is actually created that cyan color, right? Is it okay? Or yes, that green and red and blue, it has been showing 101. So red and blue is actually creating that magenta, sorry, not the cyan, magenta color. So in magenta here, we can see red and that blue is creating actually that magenta, for red and blue is creating actually the magenta, that color. So you need to actually draw that RGB space, which is actually asked in the question, and then actually mark it where actually the magenta is, okay. All right, I think maybe the time is up, and we have only one that HSV model, that one hue saturation value that we are going to discuss, okay. And that's maybe we will be done for this chapter. All right. Yes, Minhaj?
Sir, can you please extend the submission time of flag assignment?
Why?
Sir, I have so many assignment project in this week. I cannot finish yet.
So that's why the submission date should be extended.
Okay, sir. No
Recording
need.
stopped.
Sir, about
Do
the
you,
assignment,
do you understand my point? Usually a submission date has been whenever it has been defined earlier, you need to start doing a plan of view. This is also part of the assignment and your marking, right? Because sometimes you need to remember in your life that some stage will come which will not be extended, okay. So you need to consider and understand about actually the assignment, why we have an assignment. Assignment doesn't mean that actually you have a specific task and you have to do it and in a perfect manner. The thing is, it is many other things are actually relevant with it. How you are doing it,